Welcome back to mathkernel. Last time we built orthonormal bases from scratch with Gram-Schmidt, so you now have a method for producing right-angle rulers on demand. Today we step back and ask a more basic question. What is a bilinear form, the scalar product-like object underneath all of it, actually made of? The answer is a single matrix. And once you see that, every question about the form turns into a question about the matrix. A bilinear form takes two vectors and returns a number, and it's linear in each slot separately. That sounds like infinitely much information, a value for every possible pair. The surprise of today is that all of it is packed into a single square table of numbers.
So on the board I've drawn the basis E1 and E2, and two general vectors V and W built out of them. Where does the table come from?
You only ever need the form on the basis pairs. Define the entry in row I, column J to be B of EI with EJ. That's an n by n matrix, and I claim it already knows the value of B on every other pair.
That's a strong claim. One little table, and it reproduces B on all of the infinitely many pairs? Show me why it can't be missing something.
Watch bilinearity do the work twice. Feed V as a combination of the E's into the first slot. Linearity pulls the X's out front. Then expand W in the second slot. Linearity pulls the Y's out too. What's left is a double sum of Xi times B of EI-EJ times YJ.
And that double sum, that's just row vector, matrix, column vector, isn't it?
Exactly that. The sum over I and j of xi times aij times yj is precisely x transpose times a times y. So B of v and w is x transpose ay, the whole form, compressed into one matrix. So a bilinear form isn't a mystery machine, it's a matrix in disguise. Evaluate it by sandwiching that matrix between the two coordinate vectors. Now the payoff of having a matrix. Properties of the form become properties of the matrix. The first and most tested one is symmetry. The form is symmetric. B of VW equals B of WV for all inputs, exactly when the matrix equals its own transpose.
The forward direction feels easy. If swapping V and W never changes the answer, then in particular swapping the basis vectors doesn't. So aij equals aji.
That's the whole forward direction. Symmetry on the basis pairs is exactly aij equals aji, which is the matrix being its own transpose. The other direction is the fun one.
Right, going backward you only know the matrix is symmetric. How do you get symmetry for every V and W out of that? You'd have to move X and Y past each other.
And here's the trick worth remembering. B of VW is X transpose AY, but that's a 1-by-1 matrix, a single number. A number equals its own transpose. Transpose the product, and it reverses order. You get Y transpose, A transpose, X. Now use that A is symmetric, and that's exactly B of WV.
So the scalar quietly flipping into its own transpose is what lets you swap the two vectors. Sneaky.
Sneaky and reusable. Run the same argument with a minus sign and you get skew-symmetry. The form flips sign under swap exactly when the matrix is minus its own transpose. And that forces something strict on the diagonal.
Minus its transpose, so each diagonal entry equals its own negative. That pins every one of them to 0.
So the matrix mirrors the form. Symmetric matches symmetric, antisymmetric matches skew. And a skew form must vanish on the diagonal, so B of V with itself is always 0. So symmetric matrices and antisymmetric matrices are the two clean types. Here's the fact that ties them together. Any square matrix splits into one of each in exactly one way. Average it with its transpose for the symmetric half, and take half the difference for the antisymmetric half.
On the board, it's just A written as sim plus skew. Adding the two halves gives a back. The transposes cancel or reinforce as needed.
Precisely. Transpose the first half and it's unchanged. Transpose the second, and it flips sign. So one is genuinely symmetric, the other genuinely antisymmetric, and there's some rebuilds A. Now feed the same vector into both slots.
Both slots the same, that's the quadratic form, B of V with itself. Why should the split matter there?
Because the antisymmetric half contributes nothing. We just proved a skew form vanishes on every vector paired with itself, so its piece of Q is flat zero. The quadratic form only ever feels the symmetric half.
So if all I care about is V against itself, a length, an energy, a distance, I can throw the skew part away entirely.
You can, and that's exactly why, when quadratic forms and distances show up down the line, we'll always take the matrix symmetric without loss. The skew part was never visible to them. So, every form is a symmetric plus a skew half, and anything of the form V against itself sees only the symmetric one. Let's make all of it concrete. Take the form on the plane given by x1, y1, plus 2x1, y2, plus 3x2, y2. To find its matrix, just evaluate on the four basis pairs.
So each entry is B of EI with EJ. I read the coefficients straight off the formula?
Almost, and this is where people lose a mark. B of E1 is 1, B of E1 is 2, B of E2 is 3. But B of E2 that's the x2 y1 term, and there isn't 1, so it's 0, not 2. Order matters.
So the matrix has a 2 in the top right and a plain 0 in the bottom left. Prove the formula actually reproduces the form now.
Take V equals 1, 1, and W equals 2 minus 1. Straight from the definition, B is 1 times 2, minus 2, minus 3, that's minus 3. Now through the matrix, a times Y is 0 and minus 3, and X transpose against that is also minus 3. Same answer.
And because that off-diagonal pair is 2 and 0, not 2 and 2, the matrix isn't its own transpose, so this form isn't symmetric. The criterion catches it instantly.
Matrix from the basis pairs, formula verified, symmetry read off the transpose. Next we leave forms behind and ask which vectors are orthogonal to a whole subspace, the orthogonal complement. That's the matrix of a bilinear form, one table of numbers with B of VW equal to X transpose AY, and the form's symmetry mirrored in the matrices. Thanks for watching. Next time we turn from forms to subspaces, the orthogonal complement, U-perp, the set of everything at right angles to a given subspace. See you there.